Hello, everyone, and welcome to a new session of engineering statics or basic engineering. In this lecture, I'm going to discuss the first type of analysis we are going to perform in this course, which is a particle equilibrium in 2D. Wait a second. Don't ask anything. Particle equilibrium. We are not talking physics, particle stuff. No. Equilibrium in 2D. So what do we mean by particle? Particle in engineering meaning it can be a point, it can be a body, it can be a structure, but if all the forces that act on that particle or on this body are concurrent, meaning they intersect at a point, think about it, they cannot produce rotation. Notice, in the first part of the course, we'll concentrate on pure forces, only a force, a push, a pull, a weight, a tension in a cable, a force in a tie or something, but no rotation. Okay, we'll defer the rotation to later when we discuss torques. But for the time being, we are going to take an easy case where all the forces that act on a particle intersect at a point. In this case, we can ignore the shape of the body and just concentrate at the point of concurrency of these forces. And if that happens, and the body is in equilibrium, remember that Newton's first law of motion says what? Says a body in equilibrium. What's the meaning of equilibrium? Many people don't know the exact definition. Equilibrium meaning a body either at rest or moving with a constant velocity. Notice I didn't say constant speed, because if you are moving with the same speed, but say rotating or changing direction, then your velocity changes. Remember, velocity is a vector. A vector has a magnitude and it has a direction. As long as the magnitude as well as the direction are unchanged, we call that body in equilibrium. Okay? So think about it. So the body has to have the same force, meaning it has to be moving with the same speed. So there is no linear acceleration, and with the same direction. It doesn't rotate or turn right or left, meaning with zero angular acceleration. So no linear acceleration, no angular acceleration. That's why we have to be worried about two things. But wait a second. We said this is intuitive and you can prove it mathematically or engineering wise. But if all the forces acting on a body intersect at a point, this body cannot rotate. In order for rotation, at least one force has not. So if all the forces intersect at that point, but there is a force in another point, it will rotate this body. But so since they are intersecting at a point, I can ignore angular acceleration because I know there isn't any. And I have to only concentrate on linear acceleration. Linear acceleration would equal zero if all the forces cancel each other. So when I see a body in equilibrium, it's not moving in front of me. So it's definitely in equilibrium. So what are the forces acting on it? It turns out that I will have two equations of equilibrium. What is that? Because if you are in 2D, then all the forces will be 2D vectors. They have an I component and they have a J component. All the I components should add up to zero, so I don't have horizontal acceleration, and all the J component forces or the component of the J components of the forces must equal zero. They cancel each other, so I don't have a vertical acceleration. If there is no horizontal and no vertical acceleration, then there is no acceleration at all. So it's that simple. Let's take an example and I will show you why we call that a particle acceleration. Let's assume, or particle equilibrium. Let's assume we have ropes or cables that look like that. I have a horizontal one, I have a vertical one, and I have an inclined one. 3 of them. And they are connected. So this may be connected to the ceiling, and this would be connected at the wall. And here I have a mass, say, let's say anything, 40 kilogram. Also, this, I have to give you an angle. So this angle, for example, is 30 degrees. Now, you see that these three forces, one of them is known and 2 are unknown, but they all intersect at a point. So now I can ignore these whole cables and draw what we call an FBD, or free body diagram. This is the first step of solving any problem, is to draw a free body diagram. What's the meaning of a free body diagram? It means I'm going to take the body and free it from all the forces attached to it and replace these forces by the internal. I'll go in detail. Don't worry about it. In fact, if I want to solve this problem, I have to look and find 2 particles. The first one is trivial, but I'm going to use it just to show you what we have. The first particle is here, where this box is connected to the rope or to the cable. You say, that's a particle? Yes. There are 2 forces acting on it, meaning if I take this, so if I call this point A, B, C, and D, I can draw a free body diagram of particle or point A. And you say, how? Very good. First of all, this is a mass, not a force. A mass of 40 kilograms. So we are going to say the weight of this box equals the mass times the Earth acceleration, and usually we use 9.8. Okay, that's good enough. Okay, so you see the decimal place is, you can cancel it with the 0, and you just get 392 Newton. So now if I look at this point and take it away and free it from the body, how many forces act on it? If you say 2, you would be correct. 2 of them. One of them is the weight going down of magnitude 392 Newton. And what is in this cable? This cable has 2 forces. If you want to, I'm going to show them to you, and then later we'll explain them. There is a force going up here because it's keeping the body from falling down. Why doesn't the body fall down? If I cut the cable, it would fall. So something must have been pulling it upwards. It's this force. It's a force of tension. If the force is going away from the body, it's a tension. If it's going into the body, it's compression, or into the particle. So I have a tension here, but because this cable is not moving up or down, there must be another force equal and opposite to it there. This is, if I refer to it with the letter T, there is a force T here. And if I draw the free body diagram of this particle, I will see a T going down. It's a pull force. So any body or any element that is under tension, you will see 2 arrows going into each other. They seem like compressing. These are compressing. No. They're not acting on the body. This one is pulling this particle up, and this one is pulling that particle down. Notice, these are, we call them internal forces. Internal forces always come in pairs. You can't have an internal force by itself. It doesn't make sense. They have to be at least 2 forces, equal opposite and collinear. So these two are equal. They are opposite. One is going up, one is going down, and they are collinear, meaning they form a same line, because if they don't, the body will rotate. Do you see that? If you take, say, this laptop, I push it in this from this direction, and I push from the other direction, the other side, it will rotate. Any body that you push by opposite direction, you will be producing a couple that rotates things. We said we don't have any rotation in this part of the course. Usually they would let you go by assuming the tension equals 392 because it's trivial. But what I want to show you here is, if I want to write these forces as vectors, I would write this as Tj, because first of all, I have to show my axis of equilibrium. I only have forces along the y, so I don't need to show the x, right? Doesn't make sense. Why I tell you, oh, the x is horizontal? I'm not going to use it. There is no horizontal forces at all. So it's enough for me to say the y is going up. And you say, but everybody knows the y goes up. Okay, but as an individual, as a free person, I can say, I want to say my y is going down. It's fine, but I have to be consistent. I can say my y, it goes in this direction because I have forces like this force. So I say, okay, this is my y, or this is my x. It's up to me to decide. Nobody can force me to use x as horizontal and y as vertical. I can call it x prime and use an incline. The important thing is that you be consistent. When you write here, the sum of the forces in the y direction equals 0, because I only have two equations of equilibrium. Why? Because I am in 2D. When I move to the 3D, I will have three equations of equilibrium. I say all the components of the forces along the x, sum of the forces in the x equals 0, and all the components of the forces in the y equals 0. They cancel each other. This time, I don't have an x component, so I only have one equation of equilibrium. Guess what? I only have one unknown. You don't need to write a Tj minus 392j, because once we say y, meaning we are taking the j components, exactly like we did in vectors. So here I'm going to say t positive because it's the same as my y. 392 is going up opposite to the y, so minus 392 equals 0, hence T equals 392 Newton. This is trivial. Usually that they let you off the hook if you say TA here, or you call it TA to differentiate that you are showing that you are working, say, at particle A. And you say TA equals 392, they will tell you, yeah, okay, right. You don't have to show it. It's better to show it so your work would be complete. But now, since TA is known, then TB also is known. It's 392, but it's going down. Now, how many unknowns do I have at particle B? I have the force or the tension in BC and the tension in BD. So I only have two forces, but guess what? I have two equations of equilibrium. Two equations, two unknowns, I can solve. One equation, one unknown, I could solve. So next, I would say the free body diagram of point B. I usually used to tell my students, when you have three forces and two of them are unknown, definitely you know the angles, because you cannot solve more than two unknowns. If I don't give you the 30 degrees, I have to tell you the tension in this cable is that much. If I don't give you any, then you have the tension here is unknown, the tension here is unknown, and the angle is unknown. You can't. There are three unknowns and you only have two equations. That's why we solve for this tension to find out that the tension at B, so this is particle B, I have three forces. tension B, which is already known now, and it's 392 Newton. Tension BC, TBC, which is unknown, but it's horizontal. I know its direction. I dropped the root. No, I dropped the pencil. It's okay. I'm going to use it. And then I have tension BD. And I know that this angle is 30 degrees, so I have to show. Notice your free body diagram has to show all the forces and all the dimensions that are needed. If I tell you this is like 3 meters long, I don't need to show it because I'm not going to use it. But if something you would write, so here I wrote TA, I have to have TA on my free body diagram. I wrote 392, there must be 392. I said some of the forces in the Y, I must show what is my Y. Everything you use have to be on your free body diagram. Why? Because now I can cut this thing, I can cut this piece and send it to any engineer in the world. They don't need to ask me if they had to ask me, oh, what is this angle? It means I did a horrible job, a very lousy job. I didn't show my work. Okay? Notice. I'm going to draw the X and the Y like dotted like that, and I will tell you why later. But here I can solve two equations in two unknowns. You don't have to do that, by the way. I'm just showing them to you for a reason. Most people, I would say 90% of engineers, when they solve a problem like that, they will start with the summation of the forces in the Y. Think about it and tell me why. Not why, why. WHY. Think for a little bit and tell me why I shouldn't start with X. It's not wrong, but makes more sense to start with Y. Yes, if you said that TBC doesn't have a Y component, so when I do the sum of the forces in the Y, I only have one unknown, you would be right. So now I can say TBD sine 30 equals 392. So TBD would equal twice as much as that because sine 30 is 1/2. And you can get TBD very simply, it's 784. And now, because you know TBD, you can say sum of the forces in the X, equals 0. TBD cosine 30, it's positive, minus TBC equals 0, so TBC equals TBD cosine 30. You solve two equations in two unknowns, but you solve one equation at a time. If you start with the X, you will get TBD cosine 30 minus TBC equals 0. You can do anything. And then you move to the Y. So why don't you move to the Y in the first place? Nobody tells you have to start with some of the forces in the X. No, you can start with whatever. However, and that's a big however, that's what I tell my students. If you know the angles, if you have only three concurrent forces, then you definitely know the angles, but not definitely, but I can give you the angles and leave one of the angles out and give you one tension. But most of the time, you would know the angles. What is this angle? That's a 90. What is this angle? It's 90 plus 30, so it's 120. And what is that angle? Well, if everything is 360, then what is that? 150 degrees, right? 150 plus 120 is 270 plus 90 is 360. Now, you learned in high school the law of sines in trig, right? When you had a triangle, when you divide the length of every side by the sine of the opposite angle, you get a constant value. And this constant value, by the way, is the diameter of the circle where the triangle is inscribed, but that's a different story. all what I did, I had a triangle and I moved the sides to make it look like that. So now I can say, if I divide 392 by the sine of the opposite angle, which is sine 150, and some people will tell me, why you can use sine 30? Yes, you can, because 150 and 30, they are supplementary angles, and supplementary angles have the same sign. So sine 120 is sine 60. Sine 90, of course, is sine 90. Sine 45 is sine 135. Excuse me. So this is a known quantity. That's a constant. Equals TBD over sine 90, which is 1. So TBD is that. Equals TBC over sine 120 or sine 60. You can write either one. And you're done. Instead of solving two equations in two unknowns, and you were lucky because this is 1, I can use my calculator and say TBD equals 392 divided by sine 150. And you got 784 Newton, as I said, because it's like you multiply by 2. Oops. So that's the first force. So the first force was the tension in A. We found it from the first particle. And now we found TBD. And some people, because it's a force, once you say 392 Newton, you draw a arrow going down to show the direction of the force. That's, I'm sorry, in this case, it was going up. I'm sorry. It was going up like that. When you come here, TBD, you saw we draw it as an angle that makes 30 degrees. So you show the direction because TBD is a vector. And TBC is the same quantity, which is 392 divided by that, multiplied by sine 120. So I can simply multiply this by sine 120 and get TBC equals 678.96, and it's pointing to the left, Newton. You don't really need to show these arrows because on the other side, the arrow is opposite. But I'm saying at B, these are the 3 arrows that we got. And here I didn't use neither some of the forces in the X nor some of the forces in the Y, but I had to show the angles on the figure because I used the angles on the figure in my calculations. And I don't have to show my X and Y. And some people will say, no, that's an integral part of the free body diagram. No, I didn't use X. Did you see me write some of the forces in the X or the Y? No. So you cannot tell me, show me my, that's why I drew it in dash points. If I said sum of the forces in the Y equals 0, I have to show that. Notice that in this case, I would have said TBD sine 30 because we know if I know the angle between the force and an axis, then cosine would be reflecting over that axis, like what we did in the dot product. TBD sine will give me sine 30 will give me the vertical part. It's going up, so it's positive. Minus 392 equals 0. And when you solve, and because sine 30 is 1/2, you divide 392 by 1/2, and you get 784 Newton. Of course, going in that direction, but it's the same answer. And then you say sum of the forces in the X equals 0. Now, TBD is 784, but in the X direction, its component is cosine 30 minus TBC equals 0. So TBC equals 784 cosine 30. Cosine 30 is the same as sine 120 because sine 120 is sine 60 and sine 60 is cosine 30. So again, if you say 784 cosine 30, absolutely you get the same result. 678.96 Newton, exactly as before. Okay, so as you saw, the first free body diagram was really trivial because it was just the tension equals the weight. So I could have wrote that and multiply it by 9.8 and get the answer. However, I prefer to show everything so that we will be on the safe side. Even X and Y, some people, some teachers or professors would be very strict. They say, no, you have to show your coordinate x's. They may even ask you to show the x here, which is irrelevant. We never used it. I tell you, if you are not using something, you don't have to show it. But if you are using anything in your calculations, it has to be on your free body diagram. Always say, if I give this figure to some other engineer, would he or she ask me, what is this angle? Or what do you mean by X or Y? Because I didn't show my X and Y. Are you using horizontal and vertical or inclined and normal? If they ask this question, it means your free body diagram is not correct or it's not complete. Let's take another example that is more elaborate than that and see how we are going to do this. So let's draw something. Again, where is the pencil? Where did I drop it? For some reason, it disappeared into thin air, even though it's all kind of the, Okay. So let's say I have, let's get something other than angles. Say, what do you mean other than angle? Maybe an angle and a slope. So I may have two cables attached here. And I tell you, for example, this one makes an angle of 30 degrees. I was going to say 45, but it looks like smaller. This is the same wall. They are attached to this wall. But here we don't know the angle. We have a slope 3 to 4. Of course, 3, 4, you know that the hypotenuse is 5. So let's write 3, 4, 5. And then here I have another cable attached maybe to the ceiling here. And we say 3, 4, 5. Maybe we do it backwards. So we say 4, 3, 5. And then here I get some kind of weight. And let's make that in pounds. So we say 500 pounds. 500 pounds is a weight. Okay, the pound in customary units is a weight, but the kilogram is a mass. That's why the kilogram, we had to multiply it by 9.8, which is the Earth acceleration, g, to make it a weight or a force. Pound is already a force. You don't multiply it by anything. I've seen people multiplying it by 9.8, other multiplying it by 32, because that's the customary acceleration, Earth acceleration. If you are given the mass, and the mass in the customary system is in slug, if I tell you this is 10 slug or 15 slug, you multiply it by 32 to make it pounds. But usually, when we give you problems, we either give you the mass in kilogram, or sometimes they would be nice and give you the weight in Newton. And if it's a customary system, 99% of the time, they will give you the problem in pound already as a force, so you don't have to worry about that. Notice that because they give me the weight, I have to start, oh, I didn't call these A, B, C, D, E. And maybe we can call this F also, you know. This time, I'm not going to say, I'm not going to draw the free body diagram of point F and say force is 500, tension is 500, so the tension is 500. We're only going to say T equals 500 pounds and just to save time. It's now at D, I have two unknowns. I know the slope, so the direction is known, but I don't know the magnitude. I can start at D, but I cannot start at C, because at C, I have three equations, three unknowns, and there is no way you can solve three unknowns with two equations. It's impossible, right? Unless two equations are dependent, but we don't have that case here. So I will start by taking the free body diagram of particle D. And sure enough, I don't have the angles. There is no reason to say, oh, what is the angle whose tangent is 3/4, and then use 90 and whatever, because the angles would be like fractional. It's too complicated. It's better to use X and Y. So free body diagram of D, I have a force going to the left, which is tension CD. I have a force going down, which is the 500 pound. It's like the previous problem, almost identical, but I have a tension DE, and I know only the slope. It's 4.3 or 4.35. So here I have to show my X and Y. And sure enough, I use the X as the horizontal and the Y as the vertical, because I have a horizontal force and I have, I have a horizontal force and I have a vertical force. So it's easy. And because, again, this force is known, this force has both Y and X, and this only has X, then both of these have X components. So I start with the summation of the forces in the Y, like we did before. Sum of the forces in the Y equals 0. TDE is along this line. So the vertical component is 3/5 of it. That's how easy it is when you get a slope. The horizontal component is 4/5 of the force. The vertical component is 3/5 of the force. So 3/5 times TDE minus 500. Maybe we should have made that 510 so that it would be divisible by 3 and we end up with a nice number. You know what? Let's do that if you don't mind. Or 540, some number that is divisible by 3. Let's make that 510. And now you say TDE equals 510 times 5/3. 51/3 is 17, and 17 times 5 is 85. So you get 850 pounds. Then you do the summation of the forces in the X equals 0. 850, which is TDE, times 4/5 minus TCD equals 0. We said 85/5 is 17, and 17 times 4 is 68. So you get TCD equals 680 pounds. So we don't need to use calculator just to save time. So we found this guy, 510. We found this guy, 680. We found that guy, 850. Now we can move to the free body diagram of C. Free body diagram of particle C. I have the force going to the right, TCD, which is 680 pounds. I have a vertical force, notice tension, going up, TCB or BC, doesn't matter. And the slope here is 3, 4, 5. And then I have a force going down, TAC or CA, and this angle is 30 degrees, meaning that angle is 30 degrees, right? Alternate and internal. Again, here is my X, here is my Y, and I write two equations of equilibrium. Here, I have a problem. Not a problem, but because Because both of these unknown forces have X and Y components, unfortunately, I have to solve two equations in two unknowns simultaneously. I cannot solve one and one like I was lucky in the first place. So here I'm going to write the two equations. Summation of the forces in the X equals 0. I have 680 is positive minus, or I can say equals. Instead of saying minus equals 0 and then move them, I can say 680 equals, or let's leave it like that. You see that the horizontal component of TBC, which is pointing to the left, is only 3/5 of the tension. 3/5 of TBC minus TCA cosine 30, because cosine gives me the X component, equals 0. Summation of the forces in the Y equals 0. This one doesn't have a constant. It's 0, right? The TBC is going up. It's 4/5 of TBC minus TCA sine 30 equals 0. So now I have two equations in two unknowns. You see, this is negative 3/5. This is positive 4/5. So maybe I can multiply the top equation, the whole equation, by 4 and the bottom equation by 3 and then add them up. You see that? When I multiply 4 by negative 3/5, I get negative 12/5, and 3 times 4/5 is positive 12/5. So these two would cancel each other. And then when I add this, so I will get 4 times 680, got the 6, minus, here I have 4 cosine 30 plus, but I took a negative sign out, and this is negative. That's why I say plus here, plus 3 sine 30 TCA equals 0. When I move this to the, so I can say equals that. So what I did is I multiplied 4 by 680. I multiply 4 by that, so I get negative 12/5 TBC minus 4 cosine 30 TCA. And then I added to that 3 times 4/5 TBC, which is positive 12/5. That canceled the negative 12/5. 3 times that is negative 3, but I had the negative sign, so I had to add 3 sine 30 TCA. And now TCA, I can use my calculator and solve. I was going to write the equation. You don't need to. It's just, I'm going to say 4 times 680 divided by, and then I'm going to open a parenthesis and write 4 cosine 30 plus 3 sine 30, close the parentheses, and get 547.93 pound. And because I found one, I can substitute in the second equation without the multiplication. So TBC equals. Notice that this equals that. And I know TCA already, so I'm going to multiply TCA, or I'm going to divide it by 2, because sine 30 is 1/2, divide it by 2, and then divide it by 4/5. So this number, I'm going to divide it by 2. That's the same as I have multiplied it by sine 30, moved it to the other side, so it's positive, and then divide by 4/5, or multiply by 5/4. 4/5 is 0.8, so divide by 0.8, and I get 342.46 pounds. So I found all the 5 forces by using two free body diagrams. You said, but the free body diagrams solve only 4, not 5. Yes, because this one was already solved here. Notice. In fact, I had 3 free body diagram. I solved one by using the y, that the tension here is 510, and that left me with 4 unknowns. I solved 2 here and 2 there. So really, I should have used 5 equations because I didn't have an x equation at F. There was no horizontal forces like the first problem exactly. I'm sorry if that was a little too long, but we covered the 2D particle equilibrium using that. And then in our next meeting, I will try to give you a 3D particle equilibrium. Now, what if the forces are in space and they have X, Y, Z? We looked at that before, how to represent forces as X, Y, Z with I, J, K in different ways. And next time we will solve a particle equilibrium in 3D. Most of the time we would use a calculator. So I will show you how to use a calculator or matrices to solve 3 equations in 3 unknowns, so you don't waste time, because otherwise it may be too tedious. Okay, I hope this was helpful. Again, if you have any questions, please don't forget to leave them in the comments note, and I will get back to you as soon as I can. Thanks, and have a nice night or nice day.